Okay, so I want to talk about high-fidelity nano-FTIR, which is the paper where we divide two harmonics by each other, or subtract the phases. And you can get from data that looks like this to data that looks like that, where you can really put a ruler, and if you take a line profile, it's super flat, surprisingly flat. And the title, unfortunately, is a bit cryptic. Really, what we wanted to name this is indirect illumination of an AFM tip. And to illustrate this, this is the overview. So what can happen due to indirect illumination? Even if you have a sample here like gold, which is completely flat in topography, it doesn't mean that the optical amplitude signal is flat, although you would expect it. But we can make it flat using this ratio, and I will explain why this is needed, why this is possible. Yeah. Before going into the details, I would like to recommend you today, after the long day, you can go to this part of the town. There's a smaller beach. You can sit there, watch the sunset, and think about everything that you've learned. But you have to be careful, even though today it's a bit cloudy, that you are exposed all the time by the sun. But not only directly, but also indirectly, because the water is reflecting the sunlight also onto your face. So you have direct sun exposure and indirect sun exposure. If you sum them up, you get sunburn. Not today. Today is okay. The same works if you use an AFM tip. Now you have direct illumination, and you have indirect illumination, which is now a reflection at the sample surface. And if you sum those two up, you get signal enhancement. That's great. So if you're struggling with signal to noise, consider using a highly reflective sample. So this is indirect illumination. So we have in this expression for the scattered field, we have this alpha effective. That's the near-field interaction. That's taking place via this beta. This is near-field reflection coefficient. And the far fields, they take place via far-field reflection. And these two are, in general, not the same. So that's very important to realize. If you want to do modeling, you need two different expressions for these. So Vladimir was questioning if this is an effect that we can measure. So we've made here an experiment. We're measuring at these dots. It's measured on silicon and normalized to silicon. So we would expect a signal of 1. But we illuminate the tip via bornitride flake. And bornitride, it has a phonon around 1400 wave numbers, which means there's a small range where bornitride is very reflective. And this is what we can see here now. We see an increase in nano-FTIR amplitude because bornitride now reflects additional light onto the tip. So this works. You see the dashed line. We can also describe this with a far-field reflection factor. It fits very nicely. And the surprising thing is we can even see this at a distance of 10 micrometer. It's a question that Fritz was asking. How far can you see this effect? 10 micrometer. This is measured in the infrared. So I would say on the scale of the wavelength, however large your focused spot is. So in this case, we see it. It's not what we want at all. One way to, first of all, avoid this problem and to also show that it's an illumination effect is just rotate the sample so that we illuminate from the other side. And now we can see this peak that was here before, it's gone. And this is clear because there's no HPN here. So this is a quick test also for your experiments. If you think it's possible, there's an illumination effect. Just rotate the sample by 90 degrees, 180 degrees. Does anything change? If yes, then probably it's a far-field effect.
So I have a question.
Yes?
In this specific case, you think it's reflection from HBN, or it's maybe scattering something toward the substrate. Kind of, I mean, it's just silicon. There is something.
It may be scattering. I comment on this on the next slide. Here it's because this far field reflection factor, it fits so nicely. I think it's reflection and not scattering. Yeah. So it's true. I don't know. I don't know with 100% certainty what it is, because the goal was to get rid of it and not fully understand it. Yeah, and then so this is the case. So here I want to show when is this far field indirect illumination relevant and when is it not. We've seen this before in a talk. If we plot the normalized near field response, we have here the effective polarizability, which is normalized, and also the far field. And if these two terms, sample and reference, if they are the same, this just cancels out. And this happens, for example, when we are measuring, like done in this experiment. Yeah, so we are measuring here via silicon, we normalize to silicon. This far field factor is here, but it cancels out. That's the case it's illustrated here. The same happens if we have a particle. Yeah, it's essentially the same case. Here it doesn't matter how we move the sample, the indirect illumination will not contribute. If it's very thin, it's too small to notice. But in some cases, like if you measure at the inside of a thick flake or in a very unknown environment, then you have to account for these effects. And here, I show now an example. It's one from the introduction slide. It's just the gold on calcium fluoride. You would expect a really flat signal. We observe this. And for example, at position 2, we have now a very strong near field interaction. Here, this beta is 1. Very strong far field contribution is also 1. It's a very strong signal. At the edge, we have the near field is the same because we're still on the gold. But the far field is now on the calcium fluoride, which does not reflect. So it's small, and that's why here it's a smaller signal. Now the question is, why is it higher here? And this, we suspect it could be caused by a scattering at the edge of this gold, which then also illuminates the tip. And actually this is all interfering, so it's getting very complicated very easily. Fortunately, we can already see these two images, they look the same, which is because the far field contribution is the same. So if we just divide the two, very nicely, this all goes away. And this is exactly what's shown in the experiment. You just divide these two images, and you come to this result. Yeah, so it works beautifully in images. In spectra, this is the same data as before. We can also plot the ratio of different harmonics, and this peak disappears. And also, yeah, I'm not fully sure what these small things are, but they also disappear. So this works. And now the key question is, what happens with the near field signal? Does it also disappear or not? And for this, we had one slide, which I think wasn't shown yet, no? Okay, so this is s-SNOM amplitude and s-SNOM phase plotted for different demodulation orders. And if you look closely here, it's easier to see. The higher harmonics, they have a higher contrast. So if you subtract the green from the blue curve, there's something left. You don't remove all the signal. You have a much smaller contrast afterwards if you do this, but there's something left. And this is a real near-field signal that's left. And this we've shown here now experimentally. I think it's the last slide with new data. Essentially, it's the same experiment as before. We measure next to a bornitride flake, illuminate via this flake, in order to have here at 1400, this is a far-field peak. We know this by design. And then we put next to it a single virus, which has two absorption peaks here and here. So two of these peaks are real, and one of them is, well, two of these peaks are near-field peaks, and one of them is a far-field peak. And we, as control experiment, we rotate the sample. The far field peak disappears, near field peak stays. And then we plotted just the ratio of these two, of two different spectra. And we can see, first of all, the peak here from bornitride is gone. It's successfully suppressed. And what's really nice is that the spectral shape, and it's the same as we would expect. So if you compare this phase spectrum here, it has two strong peaks. With the real control experiment, it's two peaks, M1, M2. We get qualitatively the same, which means we can interpret it analogously. And this is because they are weak oscillators, and it's easier. Yes, but we also see, if you look at the scale, if before we had a signal on the order of 6 degrees, now it's on the order of 2 degrees. So this is what we lose when we do this. We need much better signal to noise when doing this. Yeah. Okay, so this is the ratio. Here it was shown that calculating this ratio, you can remove far field contributions. Can be illumination, can be scattering, can be maybe other things. But there's more things you can do with this ratio. For example, Fritz was already talking about normalizing one reference to another one instead of a reference material. So you can do that too. I would still recommend to also use a reference material. You can learn about depth of an object or thickness of an object. We haven't really talked about this yet, but different demodulation orders, they probe differently deep. So if you compare two different probing volumes, you can somehow learn about what's happening in the vertical direction of the sample. If you take this ratio, also the drift will disappear. I don't have a data showing that. So any fluctuation in the interferometer is also gone, because it's the same for all demodulation orders. If it happens that your laser turns off during the measurement, it's losing power slowly. This happened here, for example. The amplitude is just dropping down to 0. This can sometimes happen, especially in long experiments. Normally, I would measure again. This is not always possible, but you can try using this ratio to recover some of this information. And if you look at the substrate or even the contrast here, it's not affected at all, because this is essentially like an illumination effect. You have more or less power. And then one last application, which was used in the first version of the cryo-SNOM, a variant of this ratio, is that mechanical vibrations in the system, they maybe knock the tip a bit further away from the sample, which now also leads to smaller near-field signal. And such a normalization to different harmonics somehow helped reducing this a little bit. I don't know how much. Yeah. Okay. Yeah, so in summary, if you go to the beach to watch the sunset, bring sunscreen. I hope you know now s-SNOM and nano-FTIR, they are sensitive to far field and near field. You always measure both at the same time, but it doesn't always matter. So in some cases, they just cancel out anyway. In more complex cases, you can cancel them out via this ratio, or if you look at the phase, via this phase difference. The great thing is all this data is measured simultaneously. And even this works on very old data. Maybe in the past you had some data which you couldn't make quite sense out of. Maybe it's worth to just load them in Gwydion, divide them, and see what happens. Yeah, so it's surprisingly powerful. For being so simple, it's quite powerful to just plot. Yeah, and then I have one last slide where I just plot here different demodulation orders, amplitude and phase. You've seen the spectra before, but maybe by looking at these peaks, are you able already to tell which one is real and which one is not real? Which one is near field and which one is a far field? Of course, you know that these small two peaks, they are the near field signals, but the way that you can identify is that the peak height, it changes with the demodulation order. But this far field peak, it's exactly the same for all demodulation orders. And like this, you can identify already, and this is why you can remove it also. Yeah, and with this, now I'm really at the end.
Maybe I start with the question. Since it's an illumination effect, do you, check systematically how that depends on the average distance from the sample? Because that will moderate the near field, but eventually affect...
Which distance?
When you do the ratio, right? Mm-hmm. Since the effect that you are cancelling, it's due to an illumination, it is far field, right? Did you check systematically how that depends on the distance from the sample? Because the near field is affected. When you said in cryo happens by chance, kind of, but.
Oh, you mean vertical?
Yeah, the actual distance, because that is one is all far field, the other is a near field, right? So it may have some specific dependence on the tip sample distance.
No, on the tip sample distance we haven't really studied. I would expect it's the same because the tip sample distance you vary on the scale of the tapping amplitude. Let's say 100 nanometer maximum, and this is a far field effect. It's on the scale of the wavelengths. So over this 100 nanometer tapping, it's constant more or less. So I wouldn't expect a strong change.
Okay.
To some extent, you did study this when you looked at the RAM. You looked at the signature of the material below the RAM. So that's kind of distance dependence. So it is. Yeah, it is. And you see exactly the distortion of the shape as it transforms from one to another as the particle starts to move.
Does it matter which harmonics are used for the normalization? Do you have recommendations? Which best to use, which to avoid?
Yeah, I recommend dividing a higher one by a lower one, because then the peaks are still peaks and not dips. And then I always would recommend as high demodulation orders as possible, where the signal to noise is good enough. Because if you start using the lower demodulation orders, there's maybe some background contamination. You can even, I always divide it third by second or fourth by third, but you can also skip one of the harmonics. You can divide fourth by second or something like this, or even any combination of harmonics.
Yeah, you said we can use the higher harmonics for the normalization, but you said also that you recommend to use a reference sample. So what might be the problem?
What Fritz showed, he had a spectrum very broad, and then there were water lines, many small peaks, and 2 sharp lines. And by normalizing to a different harmonic, these water lines disappeared because it's just in the atmosphere. These 2 peaks, they were from tip contamination, so it was really material there. It was probed. It's a near field effect. If you normalize also to a silicon substrate, then these 2, they also disappear. Not perfectly, but yeah, depends then what's the substrate, what's the sample.
Thank you, Lars, again. When doing spectra, the goal is naturally to identify the material that we have under analysis, which means we go mostly into resonance, or whether weak or strong doesn't really matter. But what matters actually is that at resonance, the penetration, or let's say the volume fraction, density of wave is not really penetrating that much. It's absorbed really, because it's absorption. Yeah? Doesn't really get the same volume fraction as you have if you have non-resonant excitation. Does anyone take that into account, or do we just neglect for that?
I'm not sure if I understand the question.
The penetration, the volume actually that is responding from your sample to your tip backwards and to your detector is always that quantity that we are going to analyze. Mm-hmm. Now that changes as a function of wavelengths and whether or not there's
probing
resonance.
Volume below the tip.
Exactly.
Yeah.
So.
And it changes also for demodulation orders.
How? How do you mean in demodulation in the amplitude?
If you go to a higher demodulation order, you probe less.
Yeah, okay, yes. But, okay. when we do a spectrum, we don't think of actually that this is changing, right? Let's take the third order.
Mm-hmm. I think I know. I think I don't know. It doesn't change. It doesn't change because the penetration depth of the near field depends on the momentum of this near field. This could be frequency dependent, but it's dominated by the tip radius. So the same way that we have the same spatial resolution in the terahertz and the infrared. In the same way, the probing volume should be the same.
But in linearity is different, right? I mean, it's depending on the harmonic you are kind of...
No, stay with the third harmonic, but change the frequency. Okay, I agree that actually the volume, so to say, under the tip is the same, right?
Yeah,
but I'm not agreeing that actually the volume that is responding is the same.
It is. I think it is. Yeah, because it's limited by the tip radius in this case. So the momentum by the tip radius is huge, and the momentum by the wave, it's relatively small compared to that. And if you change the small part by changing the wavelength, if I understood correctly, yeah, we can discuss later.
Laterally, okay, but into the depth, no.
It's some enhancement effect. Enhancement absorption that goes in parallel. That's something not intuitive. When we started, we were surprised by this.
I think if we sit down with a piece of paper and
okay.
I'm also not 100% sure. Yeah.
Yeah, also because it's surprising you see far field by reflection and you don't see that. Yeah. Any other question? If not, let's thank Lars again. Lars is done for the day. Yeah.
Yes.